We had a great Compose conference, and here we are back on the usual schedule. We're really excited to have Lianne Lairmore present on the research she's doing with her group at Columbia on translating Haskell to hardware. If this sound, all of Haskell, right?
Yes.
Not some of Haskell, all of Haskell. So
Most
if
of
this
Haskell.
sounds hard, that's because it is, and that's why it's a research group. And that's also why this will be a good talk, because if it was easy, it probably wouldn't be as interesting a talk. So I'm excited to have it. Really quickly, we'll have more announcements afterwards. We really don't have any more talks booked for the rest of this year, including for next month. So come talk to us afterwards, or because there's only one talk, there'll be more time for informal discussion. We should let's line some things up and keep up the great record. And we'll have a few more announcements after. Otherwise, take it away, Lianne.
Hi, my name is Lianne Lairmore. I'm a Columbia PhD student, and I work with Stephen Edwards and Martha Kim. And as he said, I'm talking about translating Haskell to hardware. So this is our project. These are the people I work with. One of them's in the audience. He probably has the best picture up here. So this is Stephen Edwards, Martha Kim, Konya Ji, and myself. We're working on translating Haskell to hardware, but specifically hardware meant to run on the FPGA, which if you don't know what an FPGA is, it's okay, because I'll tell you in a couple slides. So let's talk about performance first. So this is the metrics for CPUs for the last 40 years. Starting at the top, there's transistors. It turns out that we haven't really slowed down the number of transistors that we can use, which means we can make more and more, use more and more logic on our chips. But our performance has kind of slowed down a little bit. If you look at this, it's not quite plateaued, but it's not going as fast as it used to be. Our frequency is definitely plateaued. So our CPUs aren't running as fast, or aren't speeding up as fast as they used to be. And our typical power is the same thing, but the power is really what's stopping the frequency from going up. Not sure how much you guys know about CPUs, but if you have too much power, you need power to get your frequency higher, and too much power means you need to cool it, and also there's leakage between the wires, and it's a big problem. So we've pretty much just done what this last metric is, and that's just add more cores, which is a problem in itself, because the memory coherency problem is it's kind of messy. It's hard to write parallel code. The memory system, you don't want cache misses. Basically, we need a new way to make our computers go faster than just making our CPUs better. Also, another thing we need to think about is power consumption. Is how much energy are our computers taking up? Because we don't need to charge our phone, or we don't want to charge our phone every 4 hours or 2 hours. We don't want an Apple Watch that we have to charge every couple of hours. We like our new wearable devices, but it'd be kind of annoying if you had to, like I said, charge them. And then servers, it costs money the more power you put into servers. It costs money to power them, and also costs money to cool them. So I propose, and I think a lot of people have proposed, that dedicated hardware is a solution to these problems. This is a mobile processor from Intel. It's really complex. If you notice the CPU at the top, that's the CPU. The rest of this is dedicated hardware meant to do specific things, except for maybe the cache. But so there's like a crypto engine, so hardware made exactly for encrypting and decrypting, and there's video encoding and decoding. And basically, our mobile devices is this heterogeneous chip full of hardware that's made for specific purposes, called accelerators. So changed it up a little bit. So this is an FPGA. It looks a lot like a CPU. This is the FPGA itself, because it's just a chip. This is a Xilinx one. There's like 2 companies that really make them, Altera and Xilinx. And the nice thing about these is they're hardware, but they're also software. It stands for a field programmable gate array, which means that it's an array of hardware that you can kind of program in such a way that It's really nice. It's faster than software, and it's less takes less energy than software. But you can program it over and over again, unlike ASIC or a chip that you've designed. These are used to be used in prototyping more, and I think they're being used more in acceleration design. Microsoft actually just launched a bunch of these for their Bing servers. So Bing now has an FPGA, or the servers have an FPGA that does part of the Bing algorithm to speed it up and just make it more cost efficient. So why would you consider an FPGA over an ASIC? An ASIC being application-specific integrated circuit. So a dedicated piece of hardware versus an FPGA. So one thing is cost. It costs a lot to make a chip. It costs a lot to design a chip, test a chip, and then you have to go find a company to print your chip. It's just pretty expensive, and really, you don't really see the price per unit isn't really worth it unless you're making a lot, like a lot. So it's really useful for the things on the phones, like the encryptors, decryptors, the decoders, because every phone is going to have one, so they're making tons of them. But something that maybe if you had an accelerator for your company that you just wanted to run on your servers, and you had maybe like a couple thousand servers, like that's not going to be enough to really afford to buy an ASICs. But you could run an FPGA, which would be pretty much the same cost no matter how many you use. Another reason is the developing cycle is a little shorter. This is the developing cycle for hardware, and the gray boxes, they aren't required for FPGAs because you kind of have this framework already set up and you work within that framework, which can limit you some ways, but it's also nice when you're designing because it makes it easier. And so the last thing, of course, is reconfigurability. I mentioned it before, FPGAs you can program again, and ASICs you can't. So if you had an error when you made your ASICs, you're just going to throw that in the trash because there's nothing you can do with it. If you want to upgrade your algorithm and you had an FPGA, you could do that with the same chip. If you did that with an ASIC, you'd have to go back to whoever and have them print them all over again. So here's the other thing that FPGAs get compared to a lot, and that's GPUs. I'm sure you guys have all heard of graphic processing units. They're really cool. They have a lot of power, which also means that they take a lot of power. It takes a lot of energy. There are some newer ones that are a little lower energy. They're really good at what they're supposed to do, which is SIMD, which is single instruction, multiple data. So they're really good at graphics per se, but anything basically that you're just doing the same thing on a lot of data, like a map. Like that's what they're. So they do poor on irregular data structures. They do poor on when you have like graph searches where you don't know where the data is going to come from or go to. FPGAs have a bunch of VRAMs on there that you can use in any configuration you want, and it kind of just changes the memory system dramatically because you can define the memory system, unlike the very structured GPU. In that way, it's very flexible in the way that a GPU, you could run one program and then send a next program on, and in an FPGA, it's not that flexible. You have to send a bit stream, and then you can run the same program for a while, and then it takes a while to reprogram it. Not like a day, but like at least a couple minutes, not something that you would be changing on the fly. But the one thing that people have had trouble with is that it's hard to program these FPGAs. And let's talk about why. So designing hardware today. So hardware is designed in what we call a hardware description language. And they're pretty low level. Even the ones that are used in industry today by everyone. They're composed of wires and transistors, and pretty much the languages are too. So this is an example of Verilog, which is one of the two mainly used languages. And the other one is VHDL. It's very similar. It has the same abstraction level, which if you look at this, is kind of none. So This is supposed to be scary code, so if you're not scared, then I did it wrong. But so this is, you define things within wires and registers. All these are 1 bit. This one's 4-bit. You have to define every single bit that you want to use, which makes sense when you're designing hardware, but do you really want to? So this program, it actually just counts the number of times that enable is high until a reset occurs, then it sets it back to 0. So this is how long it takes. This is the code length for counting on 1 value. Wire? Oh, it means that, I mean, it's a wire. So basically, it connects clock. What? Oh, sorry. So it connects, in this case, it's just a wire that this function is being evaluated on. So it just watches for a positive edge. So this is a built-in function, functionality for Verilog, and it watches this wire for a positive edge, and then when it sees a positive edge, it triggers this to happen. And so the timing is complex. So you have to make sure that your reset and enable are coming in when you want them to be. They can be different within a clock cycle, but if you wanted a reset to come before an enable, but it doesn't, then you're going to have a different answer. And same thing, vice versa. And so you really have to have a lot of interfaces or protocols for talking between these modules. And it's really complex. And personally, I don't want to think about it. And I don't think you guys would want to think about it either. So here is what is kind of the state of the art, I believe people are saying in hardware now, which to me is a little scary. This is a C++ library called systemc. It looks like C++, but it kind of looks like before too. This is the same program. It does the same exact thing. It takes in an enable, and if that enable is high, then it increments it and writes it out. So this one, it allows a little higher level abstraction. It has specific types for communications, so making the communications easier. But at the same time, those higher level types aren't all supported to be synthesized, which is the fancy word for can be made hardware. So it's really good for simulating and testing ideas, but it's not exactly what you want to be building in, because at the end, you're going to have to manually change this yourself to work in hardware. And it's just kind of a whole framework that you have to understand. You have to understand hardware, and you have to understand this framework to use it. There are a bunch of macros. Most of it is actually made up of macros, and if you move the macro to a different line, it actually changes the program. And if you need, like, it's just, I didn't appreciate it. So why did we decide on Haskell? Change it up a little bit. I mean, I don't have to convince you guys that Haskell's great, the best, no. But there are some specific points that we liked, like side effect free of side effects. That's really easy to reason about code when you don't have to worry about something happening somewhere else in the middle of calling a function. Also, it's inherently concurrent and race-free. So this was proven by people smarter than me. I'll believe them. Which is really nice when you're trying to do some parallel hardware, is knowing that no matter what you do, you're not going to mess up that bad. Like, you can't end up with a race condition. And then immutable data structures kind of ties into that. But it makes it easy to reason about parallel code, is knowing that you're not going to, something either exists or it doesn't exist, and it's not going to be changed when you don't want it to be. So we're not the first people to be like, hey, functional programming is really cool, and it kind of looks kind of like hardware. So there's these other projects that have been working on for like a while. MuFP actually became Lava. BlueSpec was started at MIT and is now a proprietary company. I think their language originally was Haskell, but I think it looks a little different now. Ruby was supposed to be kind of the same. There's like a Ruby library somewhere in between there. So all of these are really cool and offer like some levels of abstraction, like especially Clash, which you can actually, isn't part of GHC right now. It allows like higher order functions and type inference, some nice features, but when you're using all these tools, you're still writing hardware. You're just a person who knows how hardware works. You're using these tools to make hardware. So that's not the goal of our project. Our goal is that you're writing Haskell, you don't care or know about the hardware, and it magically becomes an FPGA program. So that's the dream. Like he said, this is a hard problem, so we'll be working on it for a little while still. So here's our overview of our compiler. So we use GHC front end, let them do some type checking and parsing and lexing. And so we use the core, which is pretty straightforward. So we kind of get a rich syntax without having to deal with that ourselves. So then we remove polymorphism. So we have to make everything tail recursive. And we remove higher order functions. And then what we have, like a combinational IR that's just basic code that has all these things missing that then needs to have explicit memory put in. The memory reads and writes need to be added. And then eventually it needs to be kind of mapped to time because functions work like per clock cycle, kind of like that Verilog code is the clock kind of tells you when you should be doing things. And then eventually we go to Verilog code, which is like Verilog with a couple fancier types. And then Cordis 2 is the Altera FPGA tool. If you use an FPGA, they're all proprietary, so they have to do the magic to turn your HDL to the net list. And then the net list can go to the FPGA, and then you have an FPGA with your program on it. It's definitely as simple as that. So I don't know if anyone here has done a lot of hardware, but here's kind of the end goal of what a program should kind of look like vaguely. So these clouds are what we consider combinational logic. They do something in zero amount of time, like adding or ands or simple things like that. These are registers, so this basically is like a nice little pipeline. This is the memory, so you have pipeline around the memory, and you kind of just, you chug away until you have an answer, then you send it on your way. So this is what our goal is, to kind of make a program that kind of looks like that. So like I said, we use the GHC front end. It has all these fancy things we don't have to support. So let's talk about removing higher order functions. So it turns out it's like if someone said, hey, here's a wire, now put a function on it, you're gonna be like, I don't know. Like, that's not how it works. So this doesn't really make a lot of sense. So luckily, this isn't our thought. We did some research, and it turns out someone already kind of figured out how to get rid of higher order functions. So we kind of used their algorithm to remove higher order functions. You have to list some lambdas. So like free variables, like here, this z is a free variable because we don't know where it's coming from. So you just get rid of that. Well, not like that, but eventually. There's some method there, but I mean, that's not the point of the talk, to talk about a bunch of transformation algorithms. But then, so then you have functions that become types. So the ones that you're going to pass around, you kind of want them to be a type. This one's kind of very, very simple example. Obviously, it's an identity function. I wouldn't really do it for that. And so if you had like 3 functions that you used that you passed to like map, then you would have like this data type would have 3 different variants, one for each of the different functions being passed. And then you have this apply that takes in one of these function data types and applies, so it basically just calls the function on the data that you know is there right now. And so like apply could pattern match on a bunch of these if you had more than one. And then this apply function just has to be used where you, in the function that gets an argument, a function argument, you would replace that with this type, and then you would just use the apply on that function. So it's not our algorithm, but it's something we need to do to get rid of higher level, higher order functions. So let's talk about removing polymorphism. It's kind of straightforward. So you kind of just say, hey, I know I'm going to use this function with this type, and I know I'm going to use it with this type, so I'm just going to make specialized functions for those two types. Like, pretty straightforward, but it's one of the steps necessary. So removing recursion, this is a pretty complex problem. There's some work done on it. We have actually a paper. This is the paper that's out if you're interested in FHW. I have a link to it on the next slide. But basically, in programming world, when you call a function recursively, you call it, and it just magically holds somewhere that you can't see, and that's the stack frame that the nice CPU does for you, or the operating system does for you. Or the compiler does for you, I guess. And it makes this nice stack frame for you. But in hardware, you don't really have that stack frame. So you try to call a function, you're like, and then you try to call it again, and you're like, that's not, yeah, I don't think that's how we're going to have to do it. But maybe if so you have this function, and you call it again and again, and you just use a stack yourself within the function, instead of having a whole stack frame, just kind of push the objects that you need to on a stack, and then you pop them back up as you come back up. Like I said, it's a really complicated algorithm. If you want to read our paper, it describes it pretty well. It's really interesting, especially the last steps to get it into Streamland. I'll give a quick overview, but if you don't understand it, like it's understandable. So like we do a pass to remove we combine mutually recursive functions. So if they're calling each other recursively, then they should just be one function with one recursive call. And then if you're like Fibonacci and you have two recursive calls, then we're just going to use CPS to order them. Does anyone know about CPS, continuation passing style? A couple people? Okay, it's some pretty cool stuff. Basically, you pass along a function, and you're just passing along the work that you want to do in the future. And you just keep, and it kind of grows on itself, and it eventually works the way up and then all the way down. And it's some pretty cool stuff. It's used pretty commonly in compilers, or at least the ones I've seen, which isn't a lot, but translate continuations into types. So basically, we have to do the same thing we did before. So we're removing the higher order functions. So we're saying, hey, these lambdas that we're building up, we're just going to turn them into types. And then we split up the recursion into two parts. The parts where you're recursing and going deeper and deeper and deeper, and basically you're pushing onto the stack, right? And then the other part, which is you're going back up the stack and using what you're, so we separate that into operations called the call and the return. And if you separate them like that, it actually means that you can kind of translate them into pushes and pops, which then we turn them into explicit memory pushes and pops, and we then map that over our memory function that I'll talk about probably in a minute or so. So that's basically how I say remove recursion, but really we're making it tail recursive, right? We don't have to do this for tail recursion. We're making the stack rights explicit each time we do it. So here's our paper, hardware synthesis from a recursive functional language. Nice long name. So if any of this is interesting to you all, you should check it out. There's a nice Fibonacci example. I know everyone likes recursive Fibonacci. It's just a really useful program. Okay, so another thing we have to worry about is, well, not really worry about, but think about is how do you represent types in hardware? So the basic ones are like, if you have an int, it's easy. You just give it 32 bits like you do in the computer. they're pretty straightforward that way. And then this one's almost as straightforward. So this is a algebraic data type, and we use a tagged union to represent it, which just means that each one of these gets their own value in a tag, which there are 4 of them, so it only takes 2 bits to represent. So we give it 2 bits for the tag bits. And then we say, which one's the biggest? Well, one of these is the biggest, and it says it takes 64 bits, so we're going to add 64 bits for the rest of it. And so we can basically fit any one of these in this memory space. And this tells us what it is, and then that means which bits are valid. A little more interesting are the recursive data types, because that's where all the money's at. You can't really do, well, you can do recursion without recursive data types, but it's not nearly as fun, and vice versa. So it's pretty straightforward how we kind of translate them into explicit pointers. So a linked list is a linked list. Instead of calling it recursively, we just give it a different name called a pointer. And then the pointer has a fixed size depending on what we decide is how big it should be. And then we know the exact size of this to put on a wire. So then after that, we have to identify memory operations. So if we do a pattern match, it turns out that that's pretty good at identifying what a read is. So if you're having a pattern match, you're like, hey, I'm looking for this type, and I have this head pointer, and I'm like, hey, can you tell me what's in this pointer? And then when you're using a constructor, it's just like writing. So it's pretty straightforward. And then the interesting part is scheduling those. So the next part is memories, apparently. But if we talk about, for a second, switch gears a little bit to sequencing these, it's regular functions without recursive data type are pretty easy to kind of bring into our timed dimension that I'll show you later. And that's because you can just kind of map them, and they're just combinational. But it's these functions that have recursive data types that we really need to schedule reads and writes, and it becomes a lot more complicated because it takes a couple of cycles to brew a read and do a write, and it just takes a little more effort. But going back to memories, so our memory system is kind of unique. Like I said before, the FPGA is basically an array with a bunch of BRAMs on it. I don't know if you know what a BRAM is, but it's just an SRAM. So it's really fast memory. It's like what you want at your fingertips, which is where it is at. And so, and the beauty of the FPGA is it's totally configurable. If you could say, like, I want a bunch of 17-bit length memories put together into this, to like 275 bits, if that made sense, I'm sure it would work. You could totally do that in FPGA. It'd be like, okay, I can do that. And then you have like 10 of those, and it would have ports to every single one of them, which is really nice if you don't have a single hierarchy memory. So we basically decided we want to put in specialized memories. So that means that this memory over here is only going to talk to the functions that use it, and it's going to only have this type in it, which means that you don't have to worry about defragmentation if you only have one type in a memory, because it's always going to fit in that empty space. It's immutable, so we will have to worry about some sort of garbage collection or worrying about where our memory goes. But since they're independent, it's here. Do you guys know how the memory system in a computer works? It's pretty simple. Actually, not really, but you have your registers, and then your cache, and your memory, and your disk. And basically, you want everything here, but sometimes it's here, and sometimes it's here, and sometimes it's here, and you really hope it's not here. But like the closer it is, the faster your program's going to run. So there's some really cool algorithms that a lot of people have thought up to try to make it here and here as much as possible. And so the cool thing about this is, so in a CPU, if you have like a quad core, you're sharing this memory system. Maybe you have your own L1 cache, probably, but everything else is shared among. So when you have your these misses, it's because you're sharing with everyone else. It's like, hey, you're like at the toy store and like, hey, I wanted this, and it doesn't work out. So if we have these dedicated memories, and we're hoping, we're planning on having some external memory because it wouldn't really make sense to only use the memory on the chip. So eventually we will have a back-end memory kind of like this, but we're going to have like caches for every single function. Like every function is like only going to have a cache for itself. So I'm really interested when we finally get our memory system up and running to do some really nice tests to really show that, hey, if you have a cache that only works for your one function and it only has data types that you want, it probably will have a lower miss ratio, right? That'll be exciting. I'm looking forward to it. We're not quite there yet. It turns out that scheduling these reason writes are kind of a pain. We're working on it. So let's talk about mapping to time. So I use the function map. I didn't mean to, but I just realized I did. So we take our lambda calculus, basically, which Haskell is a fancy lambda calculus, and we apply it to over time. And so this is just like an example of how we want to start thinking about this. So we have this expression that says we want to map this function over these times. And let's pretend that we can pass first order functions and all of that. Let's just think about like how what we have to do. So to start off with, we kind of need to build this list. Let's pretend that I know what the evaluation order is going to be in this for now. So you're pushing one onto a stack, and you push all the rest onto a stack until you get to the end of the stack. And then you have to write nil into your memory heap as the base. And then you have to pop the 10 off your stack, and then you have to write the cons with the pointer from the right. And you keep doing this over and over again. So you kind of get this time dimension here. And then from there, you pop, you read the pointer that you got at the end, and you then take the value and you multiply it, and then you push that onto another stack, and then you do the same thing. You keep reading the pointers until you get the last value, and then you push it onto the stack. And then you do it all over again. You have to write nil, and then you pop it from the stack. And so who knew that this would take so long? There's so many steps in between. I mean, like, you think about it, you kind of know. Obviously, with deforestation, you can kind of combine the two, the intermediate stages, but you kind of get an idea of how you have to sequence these. But it's not clear to me, and it's not clear to my group exactly the automatic way of figuring out how to do this. This is just kind of a little exercise to kind of think about ordering, because the order does matter, and they rely on each other, so you have to wait for your memory to respond. So talking about sequencing Haskell, here's the dirty stuff. This is the internal IR. This is what we're going to hope. We kind of started backwards. We're like, hey, this is a hardware. This is what hardware looks like if we put it in Haskell. And this is what that is. So the first thing we did was we said, well, a stream. A stream is infinite data, kind of like an infinite list, and it has like a piece of data every time, and we're going to say that each point is a clock cycle. So if we look at count starts with the value 1, and then its next value is its previous value plus 1, and well, not 0, but 1, 2, 3. So a count does 1, 2, 3, 4, 5, 6, 7. So it's pretty straightforward. And then delay count is the same thing, except for we're just going to stick something in front of it. We're going to prepend 10, which is same as here. And then we add C, which add the counts together, which is here's kind of cool, because so we're saying that this is clock cycle 0, and this is clock cycle 0, and so this one doesn't say much. This says this is the initial value, and this is a value. But here it's kind of cool, because you're like, hey, this is the previous value of count, and I knew it from here. So it's kind of like you have some state. So this is a register. This delay operator is a register. And if the stream can be really thought of as wires. So we're kind of back down to the wires and registers that we saw in the Verilog. it's all kind of boils down to it. Talk about, so here is kind of our library functions, the basics. You don't really need much more than this to make pretty much anything. I mean, you're just like the Verilog, you're gonna have to build it up slowly. So we have, like I said, the streaming, the repeat, which is pretty easy, it just repeats a value, which is maps something, a function from one stream to another. So this is how we bring combinational functions into the streaming world, is you just map them. Pretty straightforward. Zip width is just apply a function over 2 streams. So like if you wanted to add 2 streams together, just zip width. And then scanl, which is pretty cool. It basically ends up being a state machine. So the next state, so if you can kind of see it from the definition. So you have the initial state, the input stream, and f, and it's going to output the next state, where the next state is the present state, f over the present state to input stream. Okay. Sorry, I couldn't see it. Yeah, so zip width is going to combine present state and input state using this function. And then present state is the init state. So it's kind of cool. I think. Yeah, and so the last thing I want to talk about is how we represent our memories, which is just a function. It's kind of cool. It's just a function like everything else. You map the reads and writes. You map. So this is basically, this is the dirty version. We have a cleaner version up top, but basically you have write enables, addresses, and write data, and read data comes out. So it's pretty straightforward. You just say, hey, here's a stream of all of my reads and writes, and here are going to be the results, and it kind of makes this loop that we saw at the beginning. So yeah, that's basically the very building blocks that we're starting with to try to, this is where we're aiming for in all of our transformations. Okay, so here's a recap you guys should take away from this talk, which is CPUs, they're not getting faster by themselves. We need to learn how to design hardware. FPGAs are really cool hardware. Like that's the way you should take away, is FPGAs are really cool. And we need to be able to program them in a way that doesn't suck, because it really does right now. Haskell is a really cool language, and that's why we're trying to use it. I mean, there are other reasons, but we all know that the real reason is because I just wanted to write a program in Haskell. And eventually, our goal is that people like you wouldn't have a problem programming an FPGA. Not that you guys do now, but that anyone who knows how to use Haskell could eventually make their own accelerator. So, thank you. Is there any questions? Oh, I don't have anything against stack frames. Oh, yeah, this one, okay. So if we think of these as functional modules and hardware, it just doesn't really make sense. So if you think of this as like a circuit, it doesn't really make sense that you would pass f of x to another circuit. And it wouldn't make sense to then pass, it becomes an infinite size, so you don't know what the bit width of this is, and you can't have an unknown number of circuits down on your board. Circuits? The hardware circuits. Carter? Build time. So the Haskell portion isn't so is pretty fast. The Cordis is not our fault. I mean, Cordis is a top-of-the-line tool, and it's getting faster now that Intel owns Altera. But it's a hard problem. Like the people, I call them upstairs because where I work is upstairs is the algorithm people. The people upstairs say that this is a hard problem. It's a layout problem, so it's going to take a while. So so I took an embedded systems class, and it took like 4 hours to compile our decently sized program on an FPGA. Yes, from the system Verilog to the hardware netlist. Yeah, in the back. Oh, our build cycle for simulation is easy as turning on GHCI. Like. Oh, that's what I'm saying is our program actually allows you to simulate in Haskell. So I usually test all my programs in GHCI, and it works pretty fast. Well, assuming you're not trying to take like, so it ends up, you print out like as many streams as you want to feel like looking at right now. And so if you wait for like 100 streams, like, or 1,000, actually that's not a lot, like 1,000 streams, or if you do what I do and you're like looking for a certain output and it's never going to come and you crash your computer, it's going to take a while for that. But like assuming that your stream output is relatively soon, it's not that long. I have to qualify and say that we haven't gotten beyond pretty much toy examples. So we did Brescherman's algorithm, which is a line drawing algorithm, which was kind of cool, but isn't the most complex, but it was pretty much the most complex that we've done. As opposed to, I did a depth first search algorithm, which took way more code. Like if you write in streaming land, like we call it Streamland in our group, it took like 400 lines of code to write depth first search. Is there any other questions? Yes? We've looked at it. I personally wasn't one of the ones who looked into it deeply, so I'm not sure what the answer to that is other than we are not at the moment. Yes? A problem. His question was, what happens if you have infinite recursion, or just more recursion than you have memory? So the goal right now is that we're going to go to DRAM, and if you fill a whole DRAM, then that's really your own problem. But the answer is we don't really have an answer. So like I said, this is a little in progress, but right now we're kind of just assuming that it will end. Eventually, like I said, we're going to use off-chip memory, so you'll have more than like the BRAMs that are like 40K, I think, on the on the device. But is there any other questions? Yeah, so if you write in our dialect, the FHW dialect, we have a compiler that will make that into system Verilog that will compile at the moment. This is not what I wanted. This is the secret code afterwards. Yes? Oh, okay. So, so the goals of our project, so part of the kind of figuring out where we fit in, like I said, in the GPU, they kind of have a purpose. And so we're really looking at the algorithms that don't do well on GPUs and don't do well on CPUs. And so we're kind of start looking at like graph search algorithms and maybe data dependent algorithms. Like if anyone's heard of the Lone Star suite, it's a test bench suite specifically for algorithms that work really poorly on GPUs. So we're like, hey, that's where we want to start. Is like, if you do it poorly, maybe we can do it better. But like we're not gonna, if you write a crypto algorithm in our language, it probably, the resulting code won't be what people who have spent the last 10 years writing dedicated accelerators produce. But hopefully we'll have some really cool programs like I said, I've been working on depth first search and stuff like that. Yes?
So how do you model the existing special functions on chip, make them library?
So what do you mean by special function?
Let's say like
Oh, so the only, we wouldn't do something like a crypto. So basically, we're not supporting floating point. We're saying, hey, if you want to do floating point, there's a better way to do it. So it's not going to happen. So we wouldn't do something like that for crypto, but it's not something that we will support to go really fast. Basically, we're hoping that you'll write algorithms that we're trying to speed up using this, which, like I said, is kind of these algorithms that have this, basically kind of the recursive data type, kind of following like trees and graphs and lists. We're working on really speeding up like pointer lookups and stuff like that. But yes.
Yeah,
Oh.
but what I meant was, what if you have an existing function like a, like a module that's built into the chip? How do you represent it?
Okay. So right now so FPGAs have ALUs. So it does basic like addition and subtraction, but it doesn't really have any other dedicated chips on the FPGA. So if you want to use accelerators, you have to figure out how to do that with the CPU. So that's not going to be something that our FPGA isn't going to be calling other accelerators. Yes?
So like, the example of that would be like if you want to use signal processing specific operations, a DSP chip might be better than FPGA as like a
Yes. Yes. So basically, if you have to like irregular memory access is basically, if you can't really prefetch the data, then your CPU and your GPU are gonna struggle, because basically that means that you have to wait. If you didn't prefetch it, then that means then you have to do a really long call back to your memory hierarchy. So we're hoping that being memory specific for these kinds of memories, that we'll have the memory available. We're really working on an interesting memory design is what we're aiming for. But yes. So there are some numbers in the paper that we have produced. So when it comes to speed, we have some like guesstimations based on timing diagrams for the FPGA. The thing about the FPGA is you're gaining on your speed by having less clock cycles, because it's never gonna, even if you have like a high-end FPGA, it's not gonna be a 3 gigahertz FPGA clock running. So I don't, unless I have his paper up, I can click the link actually, I think. I don't know the times off. So like, these are all within milliseconds. But they're, like I said, we haven't done anything really beyond toy examples. Like these are Fibonacci, Ackman, sum of a list, I think, yeah. So it's kind of, so it takes 12.6 milliseconds to sum a 1 million size list. They aren't great numbers, but we're working on, basically, when we wrote this, we were looking at our pipeline, and our pipeline basically was making our clock cycle too slow, and we're really trying to emphasize the fastest we could get the clock cycle, and then the fewest cycles that we'll get it there. I think it, yeah. Are there any other, yes?
Do you have different compilers for different processors?
So no, it's all going to system Verilog, which, no. But eventually we will, so we've been aiming for this really kind of puny FPGA at the moment that we've been using for class. Eventually we'll be able to kind of tweak it for the FPGAs that are going to be a little bigger. We have a bigger one around, we just haven't, we have like an FPGA guy, and he's been doing other things. Is there any other questions? Or?